We are live now. Welcome, everyone, to Paleo Pod. Today, we've got a special guest, Georgia Rose, and our topic is the origin of cephalopods. Now, cephalopods originate at or near the Cambrian explosion at about 542 million years ago. And the conventional story is that they are descended from a cap shell mollusk in which the conical cap developed chambers and a siphuncle to become a buoyancy organ. Now, nautiloids and coleoids diverged at about 420 million years ago, and the now dominant coleoids, which include octopus, squid, and cuttlefishes, diverge into the vampiropoda, which are the vampire squid, and the decabranchia, while at the same time internalizing their shells. And so shell loss has occurred independently in several groups. Now, the subsequent history of cephalopods is interesting. Some of the groups develop primate-like intelligence, and this primate-like intelligence makes them kind of the smartest invertebrates ever. And we're still exploring their capabilities. For example, the New York Times just published an opinion guest essay entitled "An Octopus Took My Camera and the Image Has Changed the Way I See the World." So these are really interesting creatures, and Georgia Rose is going to tell us about their origin. Okay, Georgia, take it away.
Cadenatha are the oldest known pelagic predator, which means they swim in the open waters, um, like the waters without any coral reefs or anything like that. And they're characterized by grasping spines around their head, which reach out and grab their prey. They're, like I said, predators. They're colloquially called arrow worms, and they're see-through. So that's a very good strategy for underwater creatures who want to make it in the underwater world. It's good for them to be see-through. It's good camouflage technique. They're predatory, like I said, and they're pretty small. This is like a centimeter, pretty tiny. And they get up to about 4.7 inches, which, you know, kind of big for a worm, but still small, like compared to, whales. And they do have a poor fossil record because they are squishy, and squishy things don't preserve well. Um, awesome. So recently, a stem taxon of the Catanatha was found, named Temestra copri. So this is, if it is what we think it is, probably the oldest known pelagic predator, which is pretty cool. The specimen in the lower area is past it at ladder lager dot, and is relatively large for a Cambrian little sea worm. Is up to 30 centimeters long, which is pretty big. And it was a high trophic level, and we know that because we actually found some of its stomach contents, which is super duper cool. Or not we, but the scientists who found this and are exploring it. And the reason we know that it is a catanath is because it shares a ventral ganglion with the catanaths, which is to the exclusion of all other animal groups. And then if you look to the right, there's a picture I pulled from a research article that I read about this, detailing the fossil that they found, which is super cool. So now I'm going to be going over cephalopods, starting with what makes a cephalopod, and then their evolutionary journey into becoming who they are now, kind of. Not really so much now, more just their Paleozoic journey.
Mhm.
So they are in the phylum Mollusca. So some extinct cephalopod examples include all but 5 species of nautiloid, belemnites, which are those little dart bullet looking things that you get in a lot of fossil books, Cambrian fossil books. And then ammonites, which everybody knows. They're the big coiled things, which, fun fact, ammonites are more closely related to squids than they are to nautiloids, even though you'd think they have the same shell. They're the same phylum, taxon, everything. They're not. Well, they're the same
I think
phylum, but
that's
they're not the same, like.
That is fascinating. Real piece
species family.
of apparently convergent evolution.
Yeah, it's super cool. Super cool. The coil shells. And then even some extinct nautiloids had the curvature shells that
Mm.
we associate with ammonites as well. They don't have the weird ones though. The extant cephalopod examples are going to be the octopus, as we know, the nautilus. I said that they were extinct, but all but 5 species are extinct. We still have 5 species of nautilus, which is super cool because they're a very, very old creature, and I love old creatures that are alive today. We have the squid and we have the cuttlefish. Those are the cephalopod examples that we have today. So what characterizes a cephalopod? There are a couple things, starting with a fleshy mantle, which is where the organs are kept. It's basically like it's their squishy outer shell. It's their flesh basically. It keeps all of their organs together and keeps them together. Next, we have a radula, which is a conveyor belt-like structure. Um, in a cephalopod, it would be the beak. Or in a squid, it would be the beak. It has radular teeth in squid beaks, which conveyor belt their food into it and slice it up so it goes down and they digest it easily.
Well, a squid would have both a beak and a radula.
Oh, oh,
Mm.
cool.
Yes, so the
I
beak
thought
is
the
and the
radula was
radula is
inside the beak.
inside of it. Yeah, it's sort of like the spiky tongue.
Cool. Um, Next we have camera eyes, which is the same structure as a human's eye. You have like the polarized light coming in and it reflects back onto the brain. Psychology about how human eye works. So cephalopods that, and they're actually better than human eyes when underwater. They have super, super functional eyes. It's really awesome.
Yes, they're better than the vertebrate eye underwater, especially at depth.
Which is so cool. I always wish I could like see what a squid sees.
That
And
would
I
be
know
neat.
shrimp,
Yeah, wouldn't that be
yeah,
awesome? Yeah,
it'd be so awesome.
they'd
And
have
shrimp and
squid vision glasses.
yeah, I
I
just
see
love
your
to see
snail.
new colors. Okay, awesome. Um, so another thing that characterizes a cephalopod from all other mollusks is they don't have a muscular foot. So when you see a snail or a slug kind of inching along the ground, that's their muscular foot pulling them. So, so now we're going to be going into cephalopod evolution, which Mark, thank you for the brief overview before I started this. Yeah, I'm going to go into a little bit more depth on that.
Mm.
But Mark kind of gave the general sense of what it's like. The Precambrian, this is a little bit more of a controversial fact. I'm going to go into that a little bit more. So in the Precambrian, we have stem mollusks developing, or I said stem chitins on my presentation, but it's basically mollusks. Chitins are a form of mollusk. Um, and then the second step is the Lower Cambrian. We have the development of chambered shells from the regular mollusk. And then we go into the Upper Cambrian. We have the development of the siphuncle in ammonites. And number 3, we have the gradual loss of cephalopod shells, which I didn't put a time period. I wonder why. So we have the stem mollusks in the Precambrian. They were the first mollusks. So we have Kimberella, which developed the radula and the muscular foot and the mantle. And some examples of these chitins, they would be chitins, are Clementi chitin sonorensis and Calcarea evangelista. And I know,
Just
Mark,
a
you're the
quick
one who's
correction
doing
there. That should be Helkieria.
Calcarea,
Yeah, Helkieria evangelista.
Calcarea.
H H HAL.
Oh, okay.
Yeah, that's okay.
Oh, I'll make
Anyway,
sure to do that next time. But you're the one who's doing research into Kimberella and Clementi chiton sonorensis, right?
that's correct. Yeah, in fact, we found Clementi Cayetan on a Mount Holyoke-led expedition.
Wow, that's awesome.
Mhm.
That's super cool. I can't wait to hear more about that once you do more research. So awesome. So as I said, we have chambered shells, which developed in the Lower Cambrian. So we know that cephalopods appeared in the Cambrian from the monoplophorans, which is a group of bottom-dwelling mollusks with tall, slightly curved conical shells. An example of that would be Tenuela, which again is a Cambrian mollusk with a chambered shell. So they all lurked on the bottom, and this is the beginning of their evolution into cephalopods when they developed the chambered shell. The next thing that developed, which is really what characterized ammonites, is the siphuncle, which is a little tube that kind of filtered out fluid from the chambered shell. And this is what allowed for buoyancy. So when you see like videos, or if you've watched Life on Our Planet on the Netflix documentary, and the ammonites are floating around in the water. It's super cute. They're allowed to do that because of the siphuncle. And in or not prehistoric planet, in Life on Our Planet, a predator actually punctures the shell, which breaks the siphuncle and breaks the um waterproofness, and the ammonite just floats to the bottom and dies. Like it doesn't even eat the ammonite in the documentary. It just lets it die, which is super sad. So the first confirmed cephalopod is an ammonite named Plestrosonericis. Is that how you say it?
It would
Or
be
the yeah.
Plectronoceros.
Oh, Plectronoceros. I totally butchered that.
No,
But yeah, that's our first confirmed cephalopod that we have, and he had that siphuncle, which is what makes
it's not an ammonite though. It would
oh
probably be a nautiloid.
oh sorry. I think that's what I meant. See, I get them confused, even though I know they're totally different. But yeah, there he is. He's super cute. And then we go into the cephalopods losing their shells. So all uncontroversial Cambrian cephalopods have shells. And like most mollusks, not all mollusks, but most, like the slug you have, which lost its shells. Cephalopods have gradually lost their shells. So the ammonite became the squid, like I said, and then for some, the shell became internal. So you have the squid's beak and the cuttlefish's cuttlebone. Those are what their shells turned into. So notice how I said uncontroversial. That's because of this little guy here, Nectocaris. I'm going to go into who he is and how he affects cephalopod evolution. Nectocaris teryx was first described in 1976, and ever since then it has proven to be a controversial figure. Why? No shell, which completely takes away from everything I just went into, with the whole evolution of the cephalopod. Like a Cambrian cephalopod with no shell. How can this be? So Nectocaris was a Cambrian creature who was found in the Burgess Shale. It was around 2 to 5 centimeters long, and it was two-tentacled. And we think it was a cephalopod because it has similar structures to a squid, although this is thought to possibly be convergent evolution and not cephalopod evolution. But what really makes this creature distinct is that it has a radula, which, as we talked about, was a distinguishing feature to a mollusk and a cephalopod. So it's possible it could just be a mollusk, but it has all these features that make it look just like a modern cephalopod. So Nectocaris is similar to Wawaxia corjuda, how do you say that?
Corrugata.
Corrugata, who was widely debated on whether it was a worm or a mollusk. It was decided to be a worm, not a mollusk. But you have that same debate, so people are worried about it being a worm. Conclusions on whether or not Nectocaris was a cephalopod. I think it was a cephalopod. And here's why. Most importantly, they had radulas, which is what differentiated it from a worm or a mollusk. So there's no way I think it would be a worm. And chadonaths, which are also worms, which is what it kind of looks like a chadonath if you look back at Temestra copri. Um, it kind of looks just like
We
that.
usually pronounce that Cadenath.
Oh, sorry. Yeah. If you look at the Cadenaths, it kind of looks a lot like one, but the thing is, Cadenaths don't have that radula. And it also doesn't have that ventral ganglion that we talked about, which is characteristic of the Cadenaths.
Mm.
Um, so why would I say it's a cephalopod specifically and not a mollusk? Muscular foot, early in just mollusks, the chitons that we talked about, had muscular foots to help them move across the ocean floor. But the problem with Nyctocaris being a cephalopod is, like I said, there's a wrench in our entire idea of cephalopod evolution. But I here's my argument against this, and it's similar to the argument that we spent the entire class this semester discussing. Um, so there's a problem with the fossil record, and it's that soft body fossils aren't well preserved. So I think that there could potentially be more evidence for soft-bodied evolution that just wasn't well preserved because the Burgess shale is really special and there's nothing like it. But my explanation for this not like it does throw a wrench in our ideas, but my explanation for this being a cephalopod is that the problem with the fossil record is that soft-bodied fossils aren't necessarily well preserved. And Nectocaris was preserved, but it was preserved in the Burgess Shale region, which is kind of special. There's not really any other conditions that were like it. So you could have literally anywhere else in the entire great big giant ocean, soft-bodied cephalopods that were evolving and just were not well preserved. Or we just haven't found their preservation yet. So I think there could be a lot more evidence that wasn't preserved or we haven't found yet for soft-bodied evolution.
Yeah, I'm not certain that Nectocaris is a cephalopod, but I like the hypothesis because it's got two tentacles, right? And
Mhm.
if you look at a squid, it's got not all those things are called tentacles. Some of them are called arms. It has two long tentacles that it's used for grasping prey, like in
Mhm.
a colossal squid or the Architeuthis, um, the giant squid. They'll use those tentacles to grab fish, but then they draw them towards the arms. So it's almost as if those
Mhm.
tentacles on a modern squid are descended from the two tentacles on Nectocaris, and then the arms were added later. I could see that as a plausible evolutionary transition.
That's
So
that's kind of
I'm
what I'm
willing to
thinking.
consider I'm willing to consider the Nectocaris hypothesis that it is a cephalopod.
What do you think it is?
I think it could be a cephalopod or a cephalopod ancestor, but as you pointed out, and this poses a problem for the conventional story where it's a monoplacophorine like cap shell that develops chambers and then a siphuncle for the origin of
Mhm.
cephalopods. So that's interesting. It could be a stem cephalopod that is very precocious about losing its shell, something like that. There's a lot to learn about this guy.
Definitely. I hope to find more specimens of it. That's kind of oh well so
Good.
this this presentation was I found it on SlideSgo. It was a super awesome presentation. And then here,
List of references.
can you see?
Yes.
Yeah, here's my resources. And then there's one more page of resources where I got the the pictures of the Tenuela shell.
Right. And that's the Tanuela reference. Yeah, which that's really quite interesting that
Yes.
Halcyonellid mollusk from the early Cambrian of South Australia does seem to have chambering in it. And that would seem to support
Hmm.
the standard model. Okay, so yeah, let's just talk a little bit for a few minutes about cephalopods. Thanks for your presentation on these really interesting possibilities at the beginning of cephalopods. And oh, uh, oh, what do you think about cephalopod intelligence, and where do you think it first appears?
I have not done much research into modern cephalopods, to be honest. I'm more interested in extinct species, which is kind of dumb. I should know more about modern species, extant species.
Yeah.
But yeah, they are super smart. I would say that that intelligence probably developed somewhere just like based on how other animals' intelligence developed, Cenozoic.
Oh, you think that cephalopod intelligence would be? Ooh, what you said, that you think that cephalopod intelligence developed in the Cenozoic?
Yeah, I would say the Cenozoic, just because that's when like intelligence started to really develop in mammals. I don't really know about cephalopods, but
Right. And I would take a different view. I think that a cephalopod intelligence might have developed much earlier.
you
You
think
could be
so?
right about that. I mean, there's a lot of paleontologists who agree with you that cephalopod intelligence really appears in the Cenozoic because of competition with marine mammals and that sort of thing. But we
Mhm,
know that cephalopods go back to the Cambrian, so they were around for
mhm.
a long time. So there was a lot of opportunity there to develop a highly intelligent life form. And in 2011, Diana McMenamin and I presented evidence for a giant cephalopod in the Triassic that made a geoglyph portrait from ichthyosaur bones. In our interpretation, we called this the Triassic Kraken theory. And the theory
Oh
was,
yeah.
yeah, this hypothesis was derided by critics and imbeciles, but as I mentioned earlier, we now know that cephalopods are really smart and they are visually active. Um, as I mentioned, the New York Times just published an opinion piece on an octopus taking a guy's camera and then taking photographs of the photographer and also itself. So it was actually making a self-portrait with this camera. And there's also aquaria that have set up octopuses to do the same thing and take photographs of the tourists as they go by. So we've got some super intelligent animals. When did this intelligence develop? I think it's possible that it goes all the way back to the Paleozoic, because recall, the Paleozoic is pretty long. It starts at 240 million years ago, ends at 252 with the end Permian mass extinction. That's a lot of evolutionary time to go through. So it's possible that there were some smart cephalopods in the Paleozoic and the Mesozoic, but we might not know very much about them. You pointed out the soft body fossil problem. And what is an octopus? But basically, a completely soft bodied creature. They're so rare in the fossil record that you can take the entire octopus fossil record and put it into a suitcase. There's so few fossils. So I think there's a lot we're going to be learning about ancient cephalopod evolution and the levels of intelligence that they reached. And we also know how impressive they are today, problem solving uh, 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 invertebrates with primate like intelligence and problem solving skills. I just find them really fascinating creatures. And so I think that once again, it's the soft body fossil record we're going to have to work to learn more about these things. And it's a fascinating start if Nectocaris really is like the first squid, but it only has two tentacles and no arms. And then the later squid add those 8 arms to the two tentacles. Yeah.
I wonder
Mhm.
in the case of Nectocaris, if Necto it
Yes.
was a cephalopod, but it was also a case of convergent evolution. So you had that Nectocaris, it went extinct, and then again that squid evolved from the ammonite, and that's where those arms and tentacles came from.
Yes, I think that that's an entirely a plausible pathway. That Nectocaris represented an early experiment in squid body form, but then goes extinct and is not directly connected phylogenetically to the real squid that appeared later from the Coleoidea. Yeah, fascinating possibility. So we have a whole swarm of really interesting scientific questions to address with these creatures. So pretty fun, pretty exciting. Okay, awesome. You have anything else you want to add?
Nope.
No. Okay, great. I think we're done. Thank you for joining
Thank
us for
you, Mark.
Paleo Pod. And
Yeah, I had fun.
we will see you at the next episode. Our next episode coming up is on the dinosaurs of the Connecticut Valley, and Mark Augustini will be back with us. Okay, signing off from Paleo Pod. Thanks again, Georgia. See ya.
Thank you, Mark. See ya.
Bye now.